preserve in order to maintain it. Because since it's gone, there is no way to recover it. So one big threat to blinding retinal diseases, to blindness, are threats that damages the retina. These diseases are unfortunately increasing year by year. According to some statistics, 10% of diabetic people have DME. DME stands for diabetic macular edema. 10% of diabetic people have DME, stands for diabetic macular edema. This is a fatal disease that affects the retina and will cause blindness. The chance of having this disease increases by the increase of patient age. About 80% of all diabetic people suffers from DME. This is a value of 95 million people are having this disease. Another type of disease called AMD, stands for age macular degeneration. About 35% of US population are having this disease. This is a value of 2,088 million people in the year of 2020. There are other diseases such as CMV and DRUSEN. So, this is how people affected by these diseases are experiencing vision. So this is normal vision, this is diabetic retinopathy impact, this is AMD impact. We see that each disease affects an area of retina which will obstruct the vision. So early detection is very important for eye diseases, as early intervention can save vision or slow down the progression in loss of vision. The diagnosis is very critical and hard in some cases because the retina have very small details. For example, these images show two scans of two different diseases, but the scans show they are very similar, but they are two different diseases. The diagnosis might take up to 10 days, maybe weeks. So you have to take an appointment at your doctor. The doctor will take some scans for your retina. These scans are being processed manually by the doctor or maybe with other doctors. Then you have to wait for the result. So processing these scans are taken long. There have been some proposed approaches. So, for example, image processing. When you take an image, we put it in the computer, we apply some filters to it, and in order to find some characteristics. This is not fully automatic, especially when we have a very large number of images. Expert systems as well have been proposed. They contain some intelligence within it, but they depend only on the expertise of the expert. This is not only fully automatic. So, we have high number of threatened people of blindness, about 300 million people in the next few years. And there is no automatic solution to detect these diseases. So, as computer science students, as professors in computer science, how can we contribute in order to solve this problem? So, the aim of our work is to propose a novel classification model based on deep learning in order to detect and identify blind and retinal diseases at early stage with very high accuracy. Many of you might be questioning, is it possible to use artificial intelligence to do a diagnosis of such critical diseases? This is what we will find out. So, as an outline of our presentation, we are going to talk about the theoretical background, then move into our experiments in approaches. Finally, we are going to do some conclusions and perspectives. So, theoretical background. Now we are going to talk about the algorithms and the tools that we are going to use in our approaches. First, we are going to talk about machine learning. We all heard of this term. But what is machine learning? Machine learning is a field of study that gives the computer the ability to learn without being explicitly programmed. What does someone means by the definition is that in the ordinary programming, we used to give a computer some input, the computer does computations on this input and gives us an output. In machine learning, we are giving the computer the input associated with the output. The computer tries to find if there are patterns between the input and the output and give us a model. This model will be used for further predictions. There are two learning types in machine learning. We have supervised learning and unsupervised learning. Supervised learning refers to the side of learning where we have the output labeled for us, meaning we are given the feed and the algorithm, the input associated with the output. The output is labeled for us. So we have two types. We have classification tasks, we have regression tasks. Classification tasks are where we are going to predict some discrete value, some discrete output. So we are going to predict a class. In regression, we are going to predict some continuous value. For example, since it's very hot these days, If you are going to predict the temperature of this morning, the temperature is a continuous value, is a real value. So we are going to see a regression task. If you are going to predict either the weather today is either hot or cold, this is classification task because we are predicting two classes. Another type of learning is unsupervised learning. A supervised learning is different from the supervised learning since here the data are unlabeled. We are feeding the algorithm some unlabeled data, so the label here are not known. So the algorithm is fed with some unlabeled data. So the algorithm tries to find if there are clusters and groups within this data. Deep learning, our focus here today. Deep learning is a subset of machine learning where artificial neural nets learns from data iteratively, similarly how human learn from experience. So deep learning is using some algorithms called artificial neural nets with many hidden layers. These algorithms learn from data by experience, like human does, because when we were born, no one knows how to talk, no one knows how to walk. We all learn all these things by experience. This is how artificial neural nets are learning from data. So artificial neural nets, called neural networks because they have a structure of a network, and neural because they are inspired by neural science. We have three main types of layers. We have input layer, where composed of input neurons and brings initial data to hidden layers for further processing. We have the hidden layers. The hidden layers are the layers that does the whole computation for us, and the output layer which produces the output of the program. The convolution neural net, our focus today, is a type convolution neural net or CNN, is type of artificial neural net that have at least one convolution operation or one convolution layer within its code. In convolution neural net, we have two main types of operations. We have convolution layer, where we have some filters. These filters are specially designed to detect if there are some clusters, if there are some characteristics within the image. So the filters try to convolve over the image in order to find some characteristics and put them in a future map. Then this future map is going to be passed to the pruning layer. The pruning operation is going to divide this future map into some small kernels and return the maximum value for each kernel. This is convolutional neural nets, briefly defined. As now we have seen the algorithms. Now we are going to apply them on our data set. Approach and experiments. First, our process in this section, we are going to have an overview first on our data set, how it's composed, how it's divided. Then we do some proper pre-processing for it, apply machine learning experiments for it, then deep learning experiment, then some comparisons between deep learning and machine learning experiments, then do a model validation. First, our data set. We have used an OCT images data set. OCT stands for optical coherence tomography. This is a scanning device that ophthalmologists use to capture some scans for our retina. They give a very high definitions of images. Our data set composed of nearly 85,000 images, composed into three folders: train, test, and validation. Each subfolder is composed of 4 categories: normal, DME, CNV, and DRUSEN. This is our classes that we aim to predict. So our task here is for a given input image, we are going to decide and to classify this image according to the disease that it contains. So we have 4 classes here. Normal stands for images that doesn't contain any diseases. DME are diabetic retinopathy, CNV, choroidal neovascularization, and DRUSEN for signs of AM. This is how our data set is split. So, pre-processing phase in machine learning is very critical phase. So, we have decided to reshape the images to have a new uniform shape of 224 pixels for each width and height. We decided to do a data augmentation. So we are going to augment our data because convolutional neural nets demands a big amount of data. So we have to bring some other data to this image. So where do we find these images? So we took some original image of our data set. We generated some similar images for it and then added it to the training set. We rotated these images and made zoomed versions and horizontally fit these images. Then we added all these generated images to our training. So now we have more augmented data set. we have done some experiences of balanced data. So we made another version of our data set where all the categories have the same number of images. So machine learning experiment. We trained 2 machine learning experiments. So we shaped the images and converted them into matrix data. So we used scikit-learn Python library to apply the CCG classifier. We obtained an accuracy up to 36% only. We decided to do a more robust classifier called XGBoost. XGBoost is an ensemble learning. Ensemble learning is we are going to create some strong learners based on weak ones. And boosting is used to improve the model prediction of any given algorithm. The main idea of boosting is to add new model to the ensemble sequentially. At each particular iteration, a new weak-based learning model is trained with respect of the model ensemble learned so far. We obtained from this algorithm accuracy up to 54%. The accuracy did raise, but it's not enough. So as a conclusion, in the use of machine learning experiments, they didn't show any good results in classifying retinal diseases. So we will use more complicated architectures for better performance. Now, moving to deep learning experiment. In deep learning experiments, we apply two sections: neural network experiment and transfer learning experiment. First, let's start with neural network experiment approach. So we proposed 4 experiments, four architecture. The first architecture is an ordinary, fully connected layers, feed-forward architecture with no convolution within it. It's composed of 6 dense layers. The second experiment is composed of 3 convolution layers, each followed by finishing by 2 fully connected layers. We added to the second architecture, meaning this one, 2 regularization terms, dropout and batch normalization. We proposed finally a deep convolutional neural net. We are going now to discuss this experiment, the third one. So our experiment is composed of architecture is composed of three main layers. So the convolution layers, 3 convolution layers, 3 max Cooney layers, 2 fully connected layers, a fine layer with 4 neurons. The convolution layer with 32 filters, each of size 3 by 3, will convert over the images and extract features from them. Then put them in an output feature. This output feature is going to be passed now to the max pooling. Max pooling will reduce the dimension of this output feature by dividing it into 4 by 4 kernels, and will only consider the maximum value in the 4 by 4 window. A dropout layer with dropout rate of 0.1 means 10% of the neuron will be turned off randomly. Flatten the 3D map output from the convolution layer into 1D feature map before adding the fully connected layers, 2 dense layers, the last one with 4 neurons. 4 neurons because we have 4 classes to build it. Some models have parameters. So the batch size, the key idea here is we are not going to feed the model with all the data in once. We have decided to divide the data into very small batches. The small batches containing 80 images, meaning we are feeding the model 80 images at each time. When all the data is passed, we call this an epoch. Epoch is a parameter how many that tells the computer how many times the model aims to use the full data for training. We set it into 15 epochs. We have a main problem in deep learning is that the training time could last for maybe days, maybe weeks. So we need to decide when to start this training. So we use early stopping to monitor the validation accuracy. This early stopping is a function that monitor the validation accuracy. If the validation accuracy didn't increase in the last 10 epochs, the training will be stopped. So these higher parameters have been chosen after conducting many experiments. So result, we have obtained the result from this experiment, So this is a learning curve for both training and validation. We obtained from this experiment an accuracy up to 98.75% in validation. We have a main problem in deep learning is called overfitting. Overfitting meaning when the model is perfect while being trained, but it fails while being tested or validation. But our model here is doing a very good job, since there is no difference between validation and training accuracies. So there is no overfitting. This is a perfect fit. So we tested this model. We tested this model on our test set. We obtained an accuracy up to 98.45%, meaning 935 images have been correctly classified out of 9068 while testing. So the result shows also that the DRUSEN class, only the DRUSEN class, have been correctly classified at 100% precise. The other classes, 99 to 96%. So, a recap of neural networks experiment. This is artificial neural nets. We obtained accuracy up to 48. These are the CNN. So far, we have obtained an accuracy up to 98.75%. These are very good results indeed. But we weren't very satisfied. We wanted to go further and propose more robust architecture. So we use transfer learning. Transfer learning is related to the use of retrained model. So we have a trained model here. This model is trained on a dataset called X. After validating this model will be saved. Then we modify this model to be trained on another dataset called Y. So the pre-trained model that we aim to use in our study have been trained on a very, very large images dataset called ImageNet. ImageNet is a dataset composed of more than 14 million images, corresponding to 1,000 categories. So we have water, we have cars, we have all the objects corresponding to 1,000 categories. So each year, a group of researchers and scientists participate in this competition in order to propose a model that outperforms the past models. So we took some of these models and tuned them. What we mean by tuning them is that replacing the last output neurons to correspond to have only 4 neurons corresponding to our 4 classes. This is the idea. So we have here 1,000 categories. Now we are going to have only 4 categories. So we first tuned VGG16. VGG16 is the winner model in 2014 in ImageNet competition. We obtained accuracy up to 53% only. We decided to modify this version by adding more convolution layers. We obtained an accuracy up to 93.5%. We wanted to do more. We tuned ResNet 50, proposed by Microsoft in ImageNet classification. We obtained an accuracy up to 96.5%. We tuned a model proposed by Google. This is a very robust model. So we obtained an accuracy up to 99%. We tested this final model on our dataset and obtained an accuracy up to 99.27% in our dataset. Meaning 9061 out of 9068 images have been correctly classified. Meaning only 7 images have been incorrectly classified. This is a very interesting result. The result shows also that 3 out of 4 classes have been correctly classified at 100% precise. This is a very interesting result indeed. So recap of our obtained results so far. This is our machine learning experiment. These are convolutional neural nets and transfer learning experiment. So convolutional neural nets give spectral results instead of accuracy compared to artificial neural nets and classical machine learning algorithms. So in our dataset, they have been proposed and published 2 papers. The first paper obtained an accuracy up to 98%. The second paper have been published lately, obtaining accuracy up to 93%, meaning our models outperform these 2 published papers. This is very indeed good result indeed. So far, our models, our architectures, has outperformed machine learning experiments, outperformed 2 published related work. So this is the only 2 papers using this dataset. So this is a very interesting result. But we wanted to see if our model can do great results comparing with ophthalmologists. So in order to compare our performance of our model, we wanted to make a comparative study with diagnosis of OCT ophthalmologists and see how well our model can do. So we asked 7 doctors, ophthalmologists, to label 10 images. So we give them an image, we tell them which disease this image contains. Then we calculated the doctors have the full time to do the diagnosis. We calculated the accuracy of all the doctors. It turned out that only 1 doctor have correctly classified the 10 images. Then we tested our model by these images, and our model have correctly classified all these images, meaning our model has outperformed the diagnosis of the ophthalmologist. This is very interesting result indeed. So as training platforms, deep learning demands very robust GPUs. We use Google Colab, a free cloud GPU proposed by Google, but have 12 gigabytes of RAM and GPU. Carbon kernels as well used here. So as achievements impacts in socio-economical, our model will help to improve quality of life by preventing blindness or slowing down the progression of blindness. Our model will help to eliminate and reduce the manual inspection and diagnosis of retinal diseases. As a conclusion of these perspectives, the development of automatic system in detecting and classifying retinal diseases is a serious challenge. CNN outperforms some state-of-the-art machine learning algorithms. Deep learning can be applied to assess the ophthalmologist in making critical decisions. For further work, we aim to test our model in different data sets using transfer learning to help in diagnosing more diseases, and integrate our model into an OCT scanning device to give a quick real-time diagnosis. These are some links that we used in the slides. Thank you for your attention.